Long-run behavior. If you were to conduct this experiment many times, how many heads on average would you expect to get per toss? So we call this the expected value of the experiment. It's an average that you would expect to get over the long term. Sometimes we call it the mean of the experiment. And we use the symbol mu to denote the mean, just like we would for a population mean. To find this expected value, this mean, we would use a probability distribution table and we'd apply this formula. Mu equals the sum of x times p of x. And I'll show you how to do that with a simple probability distribution table here. Okay, so let's go back to the probability distribution table for the number of heads in two coin flips, and we already built this. There are three values of x, 0, 1, and 2, and therefore there are three probabilities for those values of x, 0.25, 0.5, and 0.25. To calculate the mean, the expected value, you're going to create a third column, and it's going to be the value of x multiplied by the value of p of x. So here you're going to take 0 times 0.25 and put the answer in the third column. Take 1 times 0.5 and put the answer in the third column, and then 2 times 0.25 and put the answer in the third column. So if you do that, those are pretty simple multiplications that you could do in your head. Sometimes you'll need a calculator for this, but these are simple enough. 0 times 0.25 is 0, 1 times 0.5 is 0.5, and 2 times 0.25 is 0.5. The expected value, or the mean, is the sum of all the values in this third column. So adding up those three values, that's what this uppercase Greek sigma tells us to do. We get a value of 1. 0 plus 0.5 plus 0.5 is 1. So to interpret this, if we were to conduct this experiment many times, we would expect on average to get one head in two flips of the coin. Okay, so most of the time we're going to see one head come out. That would be the average number of heads. So we're going to do another experiment. We're going to take everything we've learned and apply it to a different experiment just to get some practice with these concepts. So we're going to take our original probability experiment, tossing a coin 2 times, and change it to tossing a coin 3 times. And from that experiment, we're going to do everything we just learned. We're going to build a probability distribution table, build a histogram, and calculate the expected value. So when you toss a coin 3 times, let's figure out what the outcomes are by first building a tree diagram. Okay, so when we consider the probability experiment of tossing a coin 3 times, the discrete random variable is going to be, in this case, we're changing it a little bit, it's the number of tails. So x is going to represent the number of tails. Like I had said earlier that there are two variables when flipping a coin, number of heads or number of tails. So this time we're changing our variable to number of tails. Our three coin flip experiment is going to have a tree diagram that's slightly larger than the 2 coin flip because there are going to be more outcomes. So using the example of 2 coin flips and building off of it, we can build our tree diagram. So after we have our tree diagram created, we're going to use it to build the probability distribution table for all the values of x and p of x. And once the probability distribution table is complete, we are going to calculate the mean of the distribution, the expected value, and we're going to write an explanation, a verbal explanation of what that means. Once that's complete, we're going to build our probability histogram. Okay, so that's the steps that we're going to follow in constructing in doing this problem. So the first thing, the tree diagram. Let's take our 2 coin flip tree diagram, which looked like this, and extend it to having 3 coin flips. So in order to create 3 coin flips, we have to extend each of the branches from 2 coin flips into another flip. So from this heads, we are going to branch out for another coin flip, heads and tails, and then from this tail, we're going to branch out into another heads and tails. From this heads, another heads and tails, and from this tails, another heads and tails. This tree diagram represents 3 flips of the coin. We're going to build our list of outcomes to the right here. The first set of outcomes are going to be heads, 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 and we'll list that first. And then heads, heads, tails. Then heads, tails, heads. Then heads, tails, tails, and so forth. And then we would do the same thing with these branches down here. So working our way from the root of the tree all the way to the end of the branches, we're going to label all of our outcomes. And there will be 8 of them. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Now notice that there are 3 outcomes, or rather 3 letters for each outcome. That's because we have 3 coin flips in this experiment. And that would be necessary because of course you're going to have 3 different values for H and T when you flip the coin 3 times. So there are 8 total outcomes, and we're going to use these outcomes to help establish our probabilities. So at this point, once we build the tree diagram, we have to calculate, or we have to consider our values for x. Remember that x is supposed to represent the number of tails. So we look at our outcomes and we examine them and we decide what's the minimum number of tails that are possible and what's the maximum number of tails that are possible. And then we construct our distribution table using that min and that max. So the values of x at the minimum are going to be 0. At a minimum, there is 0 tails that are possible in the outcomes. And at the maximum, there are 3 tails that are possible in the outcomes. So our values of x would therefore be 0, 1, 2, and 3. So if we examine all of these outcomes, every one of them is either going to have no tails, 1 tail, 2 tails, or 3 tails. And there's no other possible values of x for this experiment. So taking those values of x now, 0, 1, 2, and 3, we use our list of outcomes to decide on the probability for each value of x. The probability of getting 0 tails, the probability of getting 1 tail, the probability of getting 2 tails, and the probability of getting 3 tails. So coming back to your outcomes, the probability of getting no tails, if you examine this list of 8, there is only one outcome where there are no tails, and it's this one right here. So the probability of getting no tails is 1 out of 8. The probability of getting 2 tails, or I'm sorry, no, I said no tails, was 1 out of 8. The probability of getting 1 tail, let's count. We've got 1, 2, 3 of the 8 outcomes have 1 tail, and therefore the probability of getting 1 tail would be 3 out of 8. And we would continue counting like this for 2 tails and 3 tails. So our answers for P of x here, 1/8 when x is 0, that comes out to be 0.125 or 12.5%. 3/8 when x is 1, that's 0.375 or 37.5%. And when x is 2 tails, it was also 3/8. And then for 3 tails, there was only one outcome for 3 tails, and that was the TTT outcome. That's 1/8, 0.125, 12.5%. So if we want to check our work, we can sum up all the probabilities in this last column, and if we do, if we sum up all the fractions, they will equal 1. Sum up all the decimals, they'll equal 1.0. Sum up all the percents, and they'll equal 100%. So that is correct. That's what we want to happen. So now that we have our probability distribution table, we want to add a third column to that table so we can calculate the expected value. We're going to call that third column x times p of x, and we're going to take the first two columns and multiply them and put them in the third column. So here's our completed first two columns. Multiply 0 times 0.125, put the answer here, and then do the same for the rest of the table. It's just some multiplication that you can do on your calculator if you have to, and you're going to put your answers in the third column. So this is the sum. These are the sums of the first and second columns. Once you have that column complete, you're going to add up those values, add up these four values, and that will give you the expected value. This is the long-term behavior, 1.5, and this represents 1.5 tails. And now we're going to interpret what that means. And here's the interpretation. If you were to conduct this experiment many times, you would expect on average to get 1.5 tails in 3 coin flips. Okay, and that would be the average expected value. Now your histogram. This part is just a graphical representation of the first two columns of your table, your probability distribution table. On your horizontal axis, you're going to label the possible values of x, and those are 0, 1, 2, and 3. X represents the number of tails. On your vertical axis, you'll label probability. Now, since our probabilities are ranging from, let's go back and take a look at our probabilities. They go from 0.125 and then 0.375. I labeled the vertical axis from 0.10 to 0.60. So 0.125 would be approximately right here, and 0.375 is approximately right here. So we label the values of x in the center of each histogram bar, and the height of each bar is that probability. So looking at this histogram, we can answer this question. If a fair coin is flipped 3 times, what's the probability of getting at most 1 tail? So since this histogram represents the experiment for flipping the coin 3 times, we only have to look at the second part of the question to answer to get the answer. The probability of getting at most 1 tail is the same as the probability of getting 0 or 1 tail, adding them together. So at most 1 would be the sum of 0.125 and 0.375. So that probability is 0.5 or 50%. And that's how you would answer a probability question based on flipping the coin 3 times.